Next group is cqed-design-ai. Actually, did we skip any group? No? Then I guess this will be the final group. And after this, we can take a short break. Our judges will quickly discuss and decide on the winners.
Oh, thank you. Thanks for all sticking around to the last presentation. We're excited to show off what we've been working on for the past day and a half. We're superconducting circuit people, so we spend some time designing superconducting circuit chips. And what we've done here is we've built a package that does totally closed loop design of a simple superconducting circuit chip. I was planning to spend a minute or two talking about what a superconducting circuit is. It's a planar chip, normally like silicon or sapphire, with metal patterned on it to create capacitors, Josephson junctions, inductors, all the things you need to create two-level systems and couple them. A previous group has done a fantastic job, so I think we can just move on.
So as a live grad student, what we do is we have a Hamiltonian we want to realize, and then we have the circuit components, and then we put them together and we do simulations. So what we have control over is the circuit dimensions and the components we choose, and then we feed it into like ANSYS as they mentioned, and then this is an example of the outcome. But this part really sucks because we are manually changing all the parameters, and then we wait hours and hours for the simulation to complete and then choose the next parameter. And it would be really nice to have MCP tools to be able to do this process and then have a closed loop in designing.
Yeah, so basically what Wendy said, what we do is we first start with a design structure and we want a desired behavior. So then in order to actually get that, we first have to like guess dimensions and then draw the design. We then simulate the design in an EM solver. After that, from the simulation data, we extract the targeted behaviors and we see if they're good enough. If they're not, we sort of loop back on this, but if they are, we output a structure with the sort of mask we want that we will write in lithography machine. But obviously, this is a time-consuming task, and we would rather have an AI MCP tool like Lucian do it for us. And for us, for this project specifically, we're working with resonators, and we basically want to guess the resonator dimensions that we need in order to target a specific frequency and coupling queue.
All right. So like we said before, this design is a pretty slow process. And the reason for this is that the electromagnetic simulation, if you were to do it the simplest thing and take your whole chip and put it into an electromagnetic simulator, is just extremely slow. And it's slow when grad students do it, but it's similarly slow when large language models do it. The good news is because we have a large language model that can access many tools, we can make the whole process much faster. And this is another thing that we've implemented in this project. We begin by coming up with the parameters that we want to target, things like resonance frequencies, coupling quality factors. We then build an MCP tool that can do fast analytical estimates that might not be accurate, but they're in the right ballpark of what sorts of lengths and widths we need in our design to accommodate this. We have our large language model optimize its design under this approximation. We can then split our design into multiple parts and do detailed electromagnetic simulations of each component. And this works well because the scaling of the runtime of one of these electromagnetic solvers is like super linear in system size. Lastly, once Lucian, our model, optimizes each component of the design with these small simulations, we do a final validation simulation of the entire design. And this is a slow process that can take tens of minutes to hours. At the end of the day, we tell the large language model what we want. The large language model sits and turns on it for a while. And what we get out is a design that gives us our intended physics. So we built a lot of stuff in this project. There's something like 50 MCP tools. And these tools talk to lots of the things that we use to actually design superconducting circuits. Tools like Fiddle and Qiskit Metal to actually do the design, or to lay out the geometry, Sonnet and HFSS to do electromagnetic simulation, and then, of course, some internal tools that we've written that do the, well, I guess to clarify, we wrote all the tools, but some tools, internal tools that don't reference other things that people have built to do things like analytical calculations of capacitance and coupling, as well as just fitting an analysis of the data that we get from simulation. So what we're going to show now is a demonstration of the full flow, designing a quarter wave superconducting resonator coupled to a feed line. That uses the tools that ended up being reliable enough to do this analysis. So we use Fiddle and our interface to Fiddle for doing the resonator design. We use Sonnet to do the analysis. And so, yeah, now we can go ahead and show you guys an example of this whole flow working.
Just to get
just to put stuff into context, what we want is something that looks like this at the end, where you have a chip. It has a bunch of resonators, which you can see because of bad aspect ratio. But when you take an optical image, what we're trying to realize is that that squiggly thing, that's our resonator, which helps us perform gates and read out state of our qubit. To send signals into that resonator, we have a feed line structure. And what the solution will do is like calculate how much coupling we want of the feed line to our resonator, how strongly you want to send signals and receive signals from our readout resonator, and through that, the qubit. So the task that we want to solve is, Lucian, can you design a resonator with frequency 4 gigahertz, which is pretty standard, coupled to a feed line with this QC, which is like a quality factor, a metric of 20K. Okay. Yeah. So so after asking this question, Lucian thinks a little bit, and then it goes into our analytical accesses our analytical formulas MCP. So it tries to calculate the spacing between our feed line and our resonator, these geometrical properties, and through so you can see it's doing an iterative calls, and it converges to a set of parameters which give a target Q and also the target frequency. So in the previous step, also you calculate the resonator length, which gives you the frequency aspect. So this is all analytical formulas which we have encoded, which we pulled out of some grad student's thesis, and now we can interface with them easily. The second part is once it has calculated those geometrical factors, now it interfaces with this CAD tool called Fiddle, and that will generate our CAD design. So this is the CAD designer generates, and now it's going to feed that into a electromagnetic simulator, a field simulator, which will calculate what exactly the QCs are, not just use the formulas, but actually do the simulation. So that simulation is this Sonnet, which is a tool like HFSS, which folks before us talked about. So once it has ran the simulation with using that separate MCP server, it gets the QC, which is around 26,000. So it's within our tolerance. The Lucian's pretty happy that it has converged to a good quality factor. And so this was just a mini problem of it trying to calculate the quality factor. In the next step, it integrates that calculation and with the full chip design. So you can see on the chip on the top right, where you have the full chip as well as the coupling part. And now this CAD is actually something that's fab ready. So you can convert that to a DXF and send that over to Wendy, who will fab it for us. But we can also, we have solved a subset of a small problem, which is quality factor. But now we want to recalculate it with the full chip, which will give a more finer estimate. Now this simulation will take a long time. So that's why we're kind of doing it at the end.
As Eesh mentioned, so the Lucian suggested we want to do a more thorough simulation to get better accuracy, like running the full chip simulation. But unfortunately, it will take like hours, and we didn't have enough time to run it. So we just not to continue, or you just ask Lucian not to continue. But here an example of a full chip simulation we ran before using Lucian. It's not the exact chip that we showed before, but you can see through this integration of these MCP tools, it helps us really generate a resonance spectrum very clearly. And then it also calls all the MCP analysis tools that we put there and do all the fittings and help us extract all the parameters. We like, for example, the coupling Q, and then you can see this is like a circle fit, which is typically used for these resonator designs. And then give us the MCP itself can give us a result. So this is our whole workflow. So this work normally will really take students hours of time sitting in front of a computer, but now we can just ask Lucian to do it for us. All we need is just to take notes when meeting with our advisors, and then send these notes into Lucian. all our advisor can get rid of us and directly put his suggestions into the solution.
And the next step in this project, we have 3 general directions. So one direction is we want to make Lucian have memory, so it knows what simulation did before. So then it will speed up our optimization. And second is currently the design generation code is written in Fiddle, which is a very light package. I wrote MCP server in Qiskit containing like multiple tools, but then it doesn't work with Lucian, and it runs out my free context window with Cloud. So, but this is definitely a future direction because we have qubit designs and like many more complicated structures. And finally, we want to also integrate it into HFSS or like Microwave Office by Amazon so that we can check across the platforms and then get a better result. Yeah, that's it. Thank you.
Questions. First one is, how did you get the internal cube for the resonator? Is it from some parameter? That's a lie.
Yeah, so I think normally for simulation, we don't really trust the internal cube value because you can't get a very accurate loss tangent for the material. So we usually get that by measuring the sample.
Yeah, and that data was also from
That's hallucination or actual simulation?
I think this just in fitting code, we fit it with both QI and QC. It will give you like onboardable QI.
Sonnet would give you some radiation loss, and that could give a like physical QI, but this result, the overall loaded Q is accurate, but the QI, if we had more time, we would fix it.
Second question is, you guys build a lot of MCP tools. Which one is the most annoying one?
Sonnet. And Yueheng should probably talk about this, but the reason is that Sonnet takes a long time to run a simulation, and MCP has a timeout after 1 minute. And so one writes some nice threading code.
There might be some tricks you could play with pacing. I don't know if the current protocol tricks like August updates, but it just takes a little bit.
Yeah, the 3-port simulations, the 3-port electromagnetic simulations that we use to to get a good estimate of the coupling quality factor are also done in Sonnet, but those don't have that problem because those simulations take like 3 seconds. The area is much smaller.
So then you're asking here is to generate a resonator and this frequency in the cube. I guess you could ask something more general. How would it?
Yeah, so at some point you get into the problem of having to define a very large number of parameters. One could imagine a more complex version of this problem that could be done with the same strategy, which is maybe build a resonator with a Purcell filter and some like loaded admittance at the end, which could represent your qubit. And that in that sort of situation, you could generate the structure, have Sonnet or your solver of choice analyze for the admittance of each of your components and optimize each of your component parameters to get you the Purcell filter tuning that you want. What sort of system are you imagining?
Well, I was just wondering, like, if I asked it to define a Butterworth filter, where would it know? How would it?
Right now, it wouldn't really. This is fairly specialized. For example, you have this analytical calculations document, and for the purpose of this project, we only really implemented calculations that would be useful when designing resonators that are capacitively coupled to other structures. One could imagine extending this to support some sort of distributed Butterworth filter. And for that, you would probably want to add analytical calculations that tell you something about how to construct the transfer function of the Butterworth filter based on, say, functions we already have to estimate capacitance between things. And you will probably need to add some geometry primitives that give the LLM some insight into how to lay out the Butterworth filter. Does anyone else have stuff to add?
So yeah, I think our focus in this presentation or when building these MCP servers is not to have LLM go through the internet where it can find, maybe it can find the transfer functions directly, but we don't know what source it's pulling it from. So we want to have a little bit of control. So we want to design these, we want to put that Butterworth transfer function in our MCP server and verify that. We have to do something as grad students. So that's a more controlled way of building this MCP server rather than pulling random stuff from. Yeah.
Any other questions? What's up, Constance?
I had a question about like how you actually impose constraints on your design and how you make sure that it's physical.
Yes. So the geometry generation code right now knows a little bit about what we can do with optical lithography. And so if you try to define a feature where the minimum size of your feature is below 2 microns, it will tell the LLM this feature is too small, you can't generate it. Similarly, there's also basic input checking. For example, you can't take your coupling structure and put it like midway through your feed line. It'll yell at you if you try to do that. And the LLM is actually pretty smart at like reading these things and being like, oh, I screwed up. My spacing shouldn't be negative. Someone else want to take this? Is this sort of oscillator structure useful in our work?
The lumped model oscillator is a specific analysis.
Yeah.
So the lumped element oscillator basically takes in the nodes of the circuit and also a junction value. So that's more useful for qubit analysis. Yeah. But in this specific project, we're not designing qubit yet, so we didn't use that method. Yeah.
Any other questions?
All right, thank you all. That wraps up our demonstration, and we're going to take a quick break.